Good morning students, myself Srishtee Chaudhary, working as lecturer in Electronics and Communication Engineering branch at Government Polytechnic College for Girls, Patiala. Today we are going to discuss large signal amplifiers. In our last lecture we discussed about the multi-stage amplifiers. The multi-stage amplifiers were the amplifiers that were cascaded or were kept in succession one after the other so that we can increase the strength of the signal. We studied various couplings in that particular lecture, for example RC coupling, transformer coupling and direct coupling. Now with these types of couplings there are two different types of amplifiers, voltage amplifier and the power amplifiers. This particular topic is about the power amplifiers. Those employs your transformer coupling to connect the interconnections of two stages that are connected in the interconnection. Now starting with the large signal amplifiers, in multi-stage amplifiers first few stages are of voltage amplifiers and the final stages of a power amplifier. Voltage amplifier raises the voltage level of the signal, whereas the power amplifiers feed large amount of power to the load. Therefore, voltage amplifiers are designed to achieve maximum voltage amplification. They are not providing you the maximum power. And power amplifiers are designed to obtain maximum power at the output. So, when we want that the maximum output should be delivered to the load, we need a power amplifier at the end stage. But when we want that our signal strength should be increased to a particular level, we need the voltage amplifiers. This is the main difference between where the voltage amplifiers are employed and where the power amplifiers are employed. When person speaks into microphone, now we are coming to the need of the power amplifiers, why the power amplifiers are employed. Here is an example. When a person speaks into microphone, sound waves are converted into electrical signal. Now if this signal fed directly, it cannot drive loudspeaker as it is of very low voltage, it is of millivolts, it cannot drive your output load circuit, that is a loudspeaker connected. Voltage level is first raised to sufficient level, that is you are raising your signal strength to a particular level for few volts by passing it through multi-stage voltage amplifiers that you have provided the cascaded or amplifiers in succession one after the other. These stages can be 1, 2, 3 as desired by you, that how much level you want to raise. Then this voltage drives power amplifier. The power amplifier is capable of delivering power to the loudspeaker. At the end, when you have achieved a sufficient level of the signal that you are increasing, after that a power amplifier is placed at the end so that you can deliver power to the loudspeaker. Now the power amplifiers. The power amplifiers are used to deliver a relatively high amount of power, usually to a low resistance load. Typical load values range from 300 watt for transmission antennas and to 8 watt for audio speakers. Although these load values do not cover every possibility, they do illustrate the fact that power amplifiers usually drive low resistance loads. Typical output power rating of a power amplifier will be 1 watt or higher. The ideal power amplifier will deliver 100% of power it draws from the supply to the load. In practice, this can never occur. Ideally, the power amplifier takes the supply voltage and gives maximum at the output, but in practice, due to some losses, it never occurs. The reason for this is the fact that the components in the amplifier will all dissipate some of the power that is being drawn from the supply. There are several reasons for the difference between the practical and theoretical efficiency ratings of the amplifier. We have discussed that ideally it should deliver the maximum, but practically it is not possible. Now there are some theoretical and practical reasons, some of are given below. As the derivation of the efficiency value assumes that your VC equivalent is equal to VCC collected voltage. In practice, VC equivalent will always be some value that is less than VCC. So that is not equivalent to your VC, EQ is not equal to VCC. In practice it is less, so it will affect your signal or power that has to be delivered. The transformer is subject to various power losses as we have discussed. Among these losses are couple losses, various losses. The transformer power losses are not considered in derivation of efficiency value. So the derivation of efficiency value is according to ideally or a theoretical procedure. In that theoretical or ideal procedures, these practical considerations are not taken into account. So in actual, the maximum power is somewhat less that is given at the output. One of the primary advantage of using the transformer coupled class A amplifier is the increased efficiency over the RC coupled class A circuit. We have discussed this RC coupled and transformer coupled in multi-stage amplifiers. The advantages of transformer coupled over RC coupled has been discussed in your last lecture. Another advantage is the fact that the transformer coupled amplifier is easily converted into a type of amplifier that is used extensively in communication, that is the tuned amplifiers. The tuned amplifier is a circuit that is designed to have a specific value of power gain over a specific range of frequency. That is, the tuned amplifiers work to a specific frequency. They provide the power gain for particular specific frequency for which they are intended to be tuned. Now the process of power amplification. Does the power amplifiers provides the power amplification? No, power amplifiers do not amplify the power. It simply takes your DC power from the supply connected to the output circuit and converts it into useful AC signal power which is fed to the load. So we can say that power amplifiers work as an converter. They converts your DC supply voltage to your AC signal. That is, your DC signal is converted into the AC signal. That DC signal or DC supply voltage is provided to the circuit in the form of VCC. This supply is converted into the AC signal by the power amplifier through a connection to an output circuit. Thus, power amplifier is a DC to AC power converter whose action is controlled by the input signal. This conversion is done by the power amplifier, but the working of this conversion is controlled by the input signal. So now, after having a brief idea about the power amplifier and the voltage amplifier, we can have a difference between a power amplifier and a voltage amplifier. The first particular to be differentiated is the coupling. We know that power amplifier employs your transformer coupling and voltage amplifier employs your RC coupling. The output power of your power amplifier is very high as compared to voltage amplifier that is very low. The collector current of power amplifier is very high, that is greater than 100 milliampere. In case of your voltage amplifier, it is very low, that is equal to 1 milliampere. The output impedance of the power amplifier is very low, 100 to 200 ohm. In case of voltage amplifier, it is high, 10 kilo ohm. The input voltage for power amplifier is 2 to 5 volts, that is high, as compared to voltage amplifier that is low, that is equivalent to 2 to 5 millivolt. The beta factor, that is the amplification factor for current for power amplifier, is low, 25 to 50. In case of your voltage amplifier, it is high, greater than 100. RC, the collector resistance is low in case of your power amplifier, that is 5 to 25 ohm. For voltage amplifier, it is high, greater than 100. The base for power amplifier is thick. As you have to deal with the larger signal values, the base has to be thick. For in case of voltage amplifiers, as it has to deal with low signal values, the base is made thin. The heat sink is provided in case of your power amplifier. It has to deal with higher current, more dissipation is there in case of power amplifier. So heat sink is a requirement in the power amplifier, whereas in voltage amplifier the heat sink is not a requirement. The impedance matching in power amplifier is excellent as we have a transformer coupling employed in the power amplifier. In voltage amplifier, there is no good impedance matching, as we know that RC coupling is employed in case of a voltage amplifier. Power amplifier works as a converter, yes, but voltage amplifier, no. Power amplifier, as we have discussed, converts your DC signal to AC signal, so it works as a converter, but voltage amplifier doesn't work as a converter. The input resistance in case of power amplifier is high as compared to voltage amplifier input resistance, that is low. Now, stages of power amplifier in a block diagram shape. We have discussed that the signal in microphone is converted into the electrical signal and it cannot be given at the output directly because it cannot drive your load circuit because the signal value is very low. It cannot drive your output circuit. So now what we need, we want that some of the voltage amplifier stages should be employed in between before your final stage of power amplifier, so that your signal should be raised to a particular level. The strength of the signal is raised. Here in the block diagram, there is shown the microphone that converts your signal into the electrical signal. This electrical signal is the input to the voltage amplifier. These voltage amplifier stages can be 2 or can be 3 as desired by you, that at what particular level you want to raise your electrical signal strength. After you have achieved the electrical signal strength to which you want to raise the signal, the output of the voltage amplifier is given to the power amplifier. Power amplifier provides the perfect impedance matching, that is, input power is equal to the output power. Maximum power is provided at the load so that it can drive the loudspeaker, that working as a load circuit here. Now, usually a practical amplifier is an audio amplifier. Its function is to amplify a weak signal sufficiently strong to operate a loudspeaker or the other devices. The power amplifier has 3 stages: voltage amplification stage, driver stage and power stage. Now we will discuss these 3 different stages in brief, what a voltage amplification stage does, what a driver stage does and what a power stage does. Now coming to the voltage amplification stage, as the name indicates, voltage amplifiers are employed in these stages. Signal received is of very low voltage level, that is less than 10 millivolt. Therefore, 2 or more voltage amplification stages are employed at start to raise the voltage level of the signal. You can employ 2 voltage amplifier stages or 3 voltage amplifier stages as desired by you, that how much level you want to increase, how much signal strength you want to increase. These stages are connected by RC coupling because of its better frequency response. As we have discussed, voltage amplifier employs the RC coupling because of their better frequency response. Now the driver stage. The stage immediately precedes the output stage is called the driver stage. It receives the signal from the last voltage amplification stage and supplies necessary power to the output stage. It can be said that driver stage is the intermediate stage between the voltage amplifier stage and the output power amplifier stage. The signal received by your voltage amplifier stage is preceded to the driver stage, and driver stage further supplies it to the power output stage. It is coupled to output stage by transformer coupling. Here in driver stage, the transformer coupling is employed. Now the last stage is the power stage. The output of driver stage is fed to the output stage. This is the final stage of the power amplifier, and load is connected to this stage through an output transformer. This stage employs class B amplifiers in push-pull arrangement. This push-pull arrangement we will be discussing in detail. Now, so performance of your power amplifiers can be defined in 3 terms, that is the collector efficiency, second is the distortion, and third is the power dissipation capability. Now coming to the collector efficiency, we know what is the efficiency. It is the output upon the input. Now collector efficiency, as the name indicates, you are calculating your output across the collector terminal of the transistor, so collector efficiency. Now coming to the collector efficiency definition, a figure of merit for a power amplifier is its efficiency. The efficiency of an amplifier is defined as the ratio of AC output power, that is power delivered to the load, to the DC input power. Now try to understand this particular definition. We know the efficiency is output upon input. Now in case of power amplifiers, we have discussed that output is in the form of AC signal and input is in the form of the DC signal. So power output is AC and power input is DC. So we can define the ratio is P out AC upon P in DC. That is, by formula it can be given as AC output power to DC input power is your efficiency. So efficiency in terms of your values, the PDC, that is the DC supply voltage given to the circuit, power is V into I, that is voltage into current. For PDC, you are having the voltage is VCC, that is the supply voltage given to the circuit. So your PDC is VCC into IC. For PAC, your output is taken across the terminal collector, that output is across the collector terminal. Now output across the collector terminal power will be V into I again. At that particular point, your V is your collector to emitter voltage. So your PAC is VCE into IC. Substituting these two values, your efficiency is VCE into IC upon VCC into IC, where your VC is RMS value of output signal voltage and IC is the RMS value of output signal current. These values can be taken into terms of peak to peak. Considering into peak to peak, your VC is equal to VCE peak to peak by 2 root 2. Similarly, IC peak to peak by 2 root 2. So now substituting this peak to peak value to your PAC. Now these two values, your VCE peak to peak and IC peak to peak, can be substituted in the value of PAC, that is VCE into IC. Substituting these two values, we are having VCE peak to peak into IC peak to peak by 8. Here this 2 root 2 multiplied by 2 root 2 is equal to 8 here. So now collector efficiency is PS upon PDC. PAC we have calculated and PDC we know that is VCC into IC. So this is the collector efficiency for your power amplifiers. As we will see, certain amplifier configurations have much more higher efficiency rating than others. This is primary consideration when deciding which type of power amplifier to use for a specific amplification. We are having different types of power amplifiers, and for what particular specific amplification, what kind of power amplifier is used depends upon the consideration we are deciding. The second performance parameter is distortion. The distortion simply means the output is not the exact replica of your input. You are giving a signal at the input. The signal received at the output is not same as that of your input. So your output is a distorted waveform. The change output means the distorted waveform. The change of output waveform from input waveform of an amplifier is known as distortion. When output wave shape is not the exact replica of the input wave shape, the amplifier is said to have introduced some distortion in the signal. For example, this is the input signal you are providing to a circuit or a component. This is a sinusoidal wave we are providing to the circuit. At the output, you are having this type of signal. Here you can see that it is clipped at the positive cycle and also at the negative cycle. So your output is not exact replica of your input. It means some type of distortion is introduced in your signal. The voltage amplifiers handle very small signals, therefore transistor act as a linear device and distortion free amplification is possible in case of your voltage amplifiers because very low or small value of signals are used. But in case of power amplifiers, they handle very larger signals, therefore power amplifiers have the problem of distortion. Third performance parameter is the power dissipation capability. Dissipation is the loss of energy in the form of heat. Power dissipation means the ability of power transistor to dissipate heat that is developed in it during the operation. So it is power dissipation capability. During the operation of your circuits, the power transistor dissipate some energy, that is loss of energy occurs in the form of heat, that is known as a power dissipation capability. The power transistors used in power amplifiers carries large current that heat up the collector junction. Rise in temperature influences operating condition of the transistor. So for this particular we need the heat sinks. As you are dealing with the larger currents, your heating up of the collector junction is there, and the rise in temperature influences your operating condition of the transistor, that it can affect your operating point or the quiescent point. So for this particular we need the heat sinks. Heat dissipation capability is not sufficient, so a heat sink is provided which improves the heat dissipation and does not allow temperature to rise beyond permissible limits. In the figure shown below, there are different types of heat sinks that are provided. In general, we can understand heat sink as that it is a kind of base that is provided to your component, that the component is placed upon that particular base so that the excess of heat is absorbed in the surroundings of that particular base. That is heat dissipated, the loss of energy in the form of heat that is dissipated is absorbed in that particular surrounding base that is provided in the form of your heat sink. Now why power amplifiers? Drive a load with higher load. Cell phone needs 1 watt of power at the antenna. The audio system needs 10 to 100 watts of power. ordinary voltage to current amplifiers are not equipped for such amplifications, so we need a power amplifier. We have discussed the power amplifiers, so we can have some characteristics of your power amplifier. It experiences small load resistance, delivers large current values, requires large voltage swings, draws large amount of power from supply, and dissipates a large amount of power, therefore it gets hot. That's why we are providing the heat sinks for power amplifiers. Now, power amplifiers are classified according to the percent of time that collector current is non-zero. That is, for what particular time your collector current is 0 or non-zero defines or differentiates your different types of power amplifiers. The amount of output signal varies over one cycle of operation for a full cycle of input signal. These are types of the class A, B and C power amplifiers that we are going to discuss in detail. Here it is just given the input and the output characteristics of different power amplifiers. In case of your class A amplifier, they provide high linearity but have low efficiency. Class B amplifiers have high efficiency but the linearity is low, whereas class AB is a compromise between class A and class B amplifier. Now, coming to the class A amplifiers, we have discussed the transformer coupled amplifier, and we know that transformer coupled amplifier employed at the AND stage works as your power amplifier. So, what a power amplifier is? It is a transistor stage that employs your transformer coupling. So, we can draw the circuit of your power amplifiers. It is a transistor stage. This is the transistor stage, single transistor stage that employs your this transformer coupling. Here you are having the transformer coupling with the turns ratio NP NS, that is the primary, secondary and secondary turns ratio. It decides how much load is effectively transmitted to your output circuit. Here there are two diagrams indicating, one is the circuit diagram of your class A amplifier, and here it is the output characteristics of your class A power amplifier, specifying x and y axis. At the x axis you are labeling the voltage, that is VCE, collector to emitter voltage. At y axis you are labeling the current, that is the collector current. This is the AC load line, where your Q point is so arranged that it is the middle of the AC load line. Here you are providing the input signal and corresponding, this is the current and this is the voltage, output voltage. Now, coming to the class A amplifiers, the power amplifiers in which the operating point is so adjusted that the collector current flows during whole cycle of the input signal are known as class A amplifiers. And for class A amplifier, biasing circuit, that is R1, R2 and RE, is so adjusted that the operating point Q lies in the middle of AC load line. Here, as we have seen that here your R1, R2, RE, these are your biasing circuits. Biasing and stabilization is provided by this R1, R2, RE, and the values of this R1, R2 and RE is adjusted so or taken so that your Q point, that is the operating point, lies in middle of your AC load line. So, collector current flows at all times throughout the whole cycle, so no part of signal is cut off. This output waveform obtained in this case is exact replica of input wave shape. So, there is no distortion. We can say the least distortion or no distortion is there, as the output is the exact replica of the input. Advantages: the output is linear, as we have discussed, the output is the exact replica of the input, so output is linear. Disadvantage is that output power is low and collector efficiency is less than 50%. Now, this collector efficiency derivation will be here in the lecture proceeding further. Coming to the first class B amplifiers, now we have discussed class A amplifiers, now class B amplifiers. The difference between class A and class B amplifiers again lie in the value of current, that current is present for the full cycle or half cycle or more than the half cycle and less than the full cycle. In class B amplifiers, the operating point is so adjusted that collector current flows only during the positive half cycle of the input signal, so it is known as your class B amplifiers. For class B operation of amplifier, the biasing circuit is so adjusted that operating point Q lies at the correct out cutoff voltage. Here again, though two changes are there. First, that your current is present only for the positive half cycle. In class A amplifier it was present for the full cycle. Second is the Q. In the class A amplifier, your Q, that is the operating point, was located in middle of the load line. Here it is lies at the collector cutoff voltage, that is 0 collector current. IC is equal to 0 if you are pointing it at the collector cutoff voltage where the IC is equal to 0. It can be said that no biasing circuit is needed in this case. Why no biasing circuit is needed in this case? Because you are not dealing with any value of current here. Your IC is equal to 0. During positive half cycle of the signal, input circuit is forward biased and hence collector current flows. Here this is the output characteristics of your class B amplifier. Here again x and y axis shows your particular labeling of voltage and current. Here is the input, here is the current that is flowing for positive half cycle, corresponding you are having the output signal. So you are providing the input, full input signal for positive and negative, but current is present for only for the positive half cycle. So it works as your half wave rectifier. Here the rectification is provided, you are providing the full input signal, but at the output you are having the signal for the half particular cycle. So what is class B amplifier providing? It is providing a kind of rectification, that is the half wave rectification. That is, but during negative half cycle of the signal, the input circuit is reverse biased and hence no collector current flows. The output obtained from class B amplifier is just like an amplified half wave rectification. So now coming to the advantages: higher power output, higher collector efficiency, but disadvantage is that it suffers severe distortion. As we have seen that you were giving the full input signal, that is positive cycle, but in output you are having the, for one particular cycle the output is there, so you are having the distortion. The output is not the exact replica of your input. Now coming to the class C amplifiers, the power amplifiers in which collector current flows for less than half cycle of the input signal are known as class C amplifiers. In class C amplifiers, some reverse bias is given to the base. The collector current starts flowing only when the base is forward biased, that is for a period less than half cycle. Here again the output characteristics of your class C amplifier: your input signal is given, but your current flows less than half cycle of the input signal. So these particular type of amplifiers, you know that there we are providing the maximum distortion the class C amplifiers is giving, but the efficiency of class C amplifiers is very high. So why we go for class C amplifiers? Your efficiency is high, also they amplify particular power gain range, so these are used for one particular tuned frequency. So these class C amplifiers can be employed in your tuned voltage amplifiers. So it is an advantage for your class C amplifiers. These are used as tuned amplifiers. Higher collector efficiency is there. Now coming to the class AB amplifiers, it is the compromise between your class A and class B amplifiers. The power amplifiers in which operating point is so adjusted that the collector current flows for more than half cycle but less than full cycle of the input signal are known as your class AB amplifiers. The operating point Q lies near the cutoff voltage. For small negative half cycle and for complete positive half cycle, input circuit is forward biased, hence the collector current flows. But for small portion of negative half cycle, input circuit is reverse biased and hence no collector current flows. This is again the output characteristics of your class AB amplifier. Here you are having the input signal, your current is present for more than positive half cycle but less than full cycle, and corresponding you are having the output. So we can differentiate between class A, B, C and class AB amplifiers. Now how we can differentiate between the class A, B, C and class AB amplifiers? The first difference is between the current. For class AB amplifier, your current is present for the full cycle. For class B amplifiers, it is present for the half cycle. For class C amplifiers we have discussed that it is less than half cycle. It doesn't complete even your positive half cycle. For class AB amplifiers, the current is present for more than positive cycle but less than full cycle. You are not completing your full cycle. For example, this was your full cycle, it doesn't complete your full cycle. Second difference is of your Q point. For class A amplifier, your Q point was in middle of your load line. This is your load line. For class B amplifiers,